Hello, in this video I'm going to talk to you about what a derivative is, the limit definition of a derivative, and I'm going to introduce this to you by the infamous slope of a tangent line problem. Okay, so in this little applet here I've got a nice curve happening, and then I also have a point here and a point here. And what I want to do is I want to figure out if I had a line like this, what's the slope of that tangent line? That line is only touching the graph in one spot. Well, we know it's a little difficult to figure out the slope of a line when you only have one point. If you have 2 points, it's a piece of cake. Change in y's over change in x's. y2 minus y1 over x2 minus x1. You guys have been doing this since Algebra 1. Okay, so if you have a secant line, it's really easy to find the slope of that. But when you only have 1 point, and you're just touching the graph at 1 point, it makes it a little more difficult. But if we take the whole idea of a limit, which is what we just got done studying for 2 weeks, and look at it this way. So think of the slope as the change in y's over the change in x's. So what I'm going to do is I'm going to make my change in x, so my change in x is my distance here, right, from here to here. So I'm going to make my change in x smaller and smaller and smaller. As I make my change in x smaller and smaller and smaller, I'm getting closer to the slope of the line at the tangent point. Check it out. So here, this right here, this h equals 1.5, that's the distance between, the horizontal distance between those 2 points. So I'm going to make that smaller. So as I move that point to the left along that curve, my x distance is getting smaller. My denominator of my slope is getting smaller. As it gets smaller, as you can see, I'm getting closer and closer to an actual tangent line. So if I find the slope, to find the slope of these secant lines, we always have 2 points. So basically you're doing the change in y's over the change in x's. So what I'm doing is I'm making my change in x smaller and smaller and smaller. So what I'm doing is I'm finding the limit as the change in my x approaches 0 of a slope. Okay? That's what I'm doing. I'm finding the limit as x, the change in my x approaches 0, okay, of basically the equation of a slope. Okay, so let's put that in some mathematical terms here. So here, right here, and this, you have this in your packet, this is the definition of a tangent line with slope m. So what this really says, I know it looks really scary and crazy, that if we take what this is telling you, this is the change in y's over the change in x's. That's what this is. This is the point at C plus delta x minus the point at C. So what you have here, and let me see if I can find another graph. I think I have one here. So here's a graph. I'll make this a little bit bigger. So what you're finding here, like this is the point at C. I'm sorry, this is the point at C, and this is the point at x of f of x plus c. Okay? And this is the difference. This is our difference in our x's. Okay? Put that back. Come look at this again in a minute. Okay, so what we're going to do here is we're going to apply this limit formula to this function. To this function right here, 2x minus 3. Now we know by looking at this that the slope, this is a line, the slope is 2, right? We can tell totally by looking at this. So we're going to prove that with this limit definition of a derivative. So we want to know what the slope of the line is at this point, okay, 0.21. So what we're doing is we're going to find our x is 2. So we're going to take our c is 2. We're going to take our c, which is 2, plus delta x, which is the change in x, and we're going to plug that into our function. So basically what we're doing is we're taking 2 plus delta x and plugging it in for x right here. Okay? So this is 2 times 2 plus delta x. I plugged in 2 plus delta x, c plus delta x, in for x. Then I'm going to subtract off 3. because that's just part of my function right there. That right here, this part right here, oops, that was really ugly. You get the idea. This part right here is this part, okay? Minus whatever my function is at C. So what is my function at C? We know it's at 1, right? But I'm going to take 2 and plug it in. C is 2 in this situation, okay? That over here. C is 2. I'm going to take that and plug a 2, this in red, in for C. And that's what this is. I plugged 2 in for C, and there it is right there. And that's this part. Okay? And then we got delta x down there. So when you simplify this, you multiply it out, use a distributive property. You got 4 plus 2 delta x minus 3 minus 4 plus 3. So when you simplify all this out, you end up, you get 4 minus 4, negative 3 plus 3. Those are gone. Those cancel each other. Those cancel each other out. So you're just left with 2 delta x. Well, we know that that cancels. So the limit as x approaches 0 at 2 is 2. Okay? And we knew the slope was 2. We could tell that. This is just a line. Okay? What we can do is take this a little bit further and try to find the derivative of a function, period. So this is what this is going to do is instead of our answer being a number, being an actual slope, because if you find the derivative at a particular point, you're finding the slope at that particular point. If you do that, you're actually going to get a number for the slope, okay? If you are finding the derivative of a function, you're actually going to get a function when you're done. And you could pick any point on your function, plug it into the derivative, and find the slope of the tangent line at that point. So to save some time, this is actually in your packet as well. I'm going to walk you through this limit definition of a derivative. So what's happening, this is the same idea, this is just generalizing it. Instead of actually having a point C, like we did in the other, we're just going to have x a variable. So I've got f, the function f of x plus change in x. So this is basically one point, the y value of one point on the graph, minus another point, the y value of another point on the graph. And then delta x is the change in x, which is basically what the denominator of the slope is. So what we're going to do is find the limit as that change in x gets smaller and smaller and smaller and approaches 0. So here's the function we're going to use right here. And what we're going to do, this is the limit definition right here, it's just rewritten. We're going to take our delta x plus delta x and plug it in for our x, okay, in 2 spots. This is a pretty ugly equation, okay. The algebra's been done for you, so bear with me. So as you can see, this is just plugged in for x cubed, and then it's plugged in for x. So this part right here in these brackets is this part right here, okay? Then, I'm going to change it to blue, we're going to do minus just the function. So here's minus the function. This is just the function. We're subtracting just the function. Now when you multiply this out, and this is pretty ugly, it's been a while, probably since you've done multiplying x plus delta x times x plus delta x plus x times x plus delta x. But when you use the distributive property and multiply that out, you're going to get this right here, and then we're going to subtract x cubed and subtract 2x. So this part right here is just this subtraction. Then you're going to see, does anything cancel out? Does it help me in any way, shape, or form? So some things are probably going to cancel. So we have our x cubes are going to cancel. You might notice that. Let me get a different color. X cubes will cancel. And you have 3x squared delta x plus 3x delta x squared plus delta x cubed plus 20x. Now you can factor out a delta x, okay, which is right here. And you are left with 3x squared plus 3x times delta x squared plus 2. So when we do that, this will cancel with this. So we're just left with this polynomial. Now when you're finding the limit, remember we're just going to plug 0 in for delta x. So we plug a 0 in here, a 0 in here, and we're left with 3x squared plus 0 plus 0 plus 2, which is just 3x squared plus 2. So this is the derivative of this function. And if I wanted to pick any point on this function, like let's say I wanted to pick the point 2 on this function when x is 2. When x is 2, I want to know what the slope of the line, of the tangent line, excuse me, at x equals 2 is. So I would just plug 2 in for x, and I would get 3 times 4, plus 2, so I've got 24. So the slope at 2 of this function of the tangent line is 24, okay? I promise you will get used to this. What we have up here is just some notation. This is how you're going to see some derivatives, the notation for derivatives. F prime x, that's very popular, and y prime, very popular. We will be using dy dx quite a bit as well. Basically, dy dx, if you think about it, just stands for change in y over change in x. Okay, difference in y over difference in x, and that's what a derivative is. A derivative is a slope. That's what you just got to remember. A derivative is a slope.